So when we represent a chemical reaction, we normally draw reactants to the left of the equation and products to the right of the equation. And we use an arrow to separate the reactants from the products. So if your arrow is pointing towards the products, then I know that my products are forming. If the arrow points towards the reactants, then I know that the reactants are forming. And if I have a double arrow like this means that the reaction rate towards the right is equal to the reaction rate towards the left. So that will be called an equilibrium arrow, and your system will be set to reach a state of equilibrium. So to explain the state of equilibrium, let's look at the concentration graph. Here I am showing the reaction. This is the same reaction. Hydrogen and iodine reacts to form HI. So we know that this is the reactants, right? So the reactants are going to react with each other. And as the reactants react with each other, the concentration of the hydrogen is going to decrease and the concentration of the iodine is going to decrease because it's a reaction. Both of these concentrations are going to decrease, and as their concentration decreases, as the concentration of the product is going to increase. And this is what the concentration diagram shows. This is my reactants, so it's showing that the concentration of the reactants is decreasing. And as the concentration of the reactants is decreasing, the concentration of the product is increasing. It will reach a time where the concentration of the products of the reactants first. So the concentration of the reactants is going to reach a time where it's going to remain constant. So the concentration of the hydrogen, the concentration of the iodine, this is I2. This is going to remain constant. Let's put I2 there. This is going to remain constant over time. And the concentration of the product also is going to remain constant over time. So this one is going to remain constant over time. So again, when the concentration of the reactants decrease and the concentration of the products increase, it will reach a time where the reactants cannot decrease in concentration anymore. The products cannot increase in concentration anymore. So the reactant concentration and the product concentration is going to remain constant. This is called a state of equilibrium. We can show this in the reaction rate diagram in there, where you can easily see that this is the rate of the forward reaction and the rate of the backward reaction. When you're looking at any chemical reaction, this is the forward, this is the backward. Okay, so the rate of the forward reaction shows that hydrogen reacts with iodine. So hydrogen is going to react with iodine and their concentration is going to decrease. And you're going to reach a point in here where the concentration remains constant over time, or the reaction rate remains constant over time, since this is a rate graph. Here, the rate of the reaction is going to increase for the backward reaction. And it's going to reach a time where it's going to remain constant over time. So at this point in here, I would say that the reaction has reached equilibrium. And equilibrium means that I cannot decrease the concentration of the reactants anymore, and I cannot increase the concentration of the product anymore. So both, they have a constant, not equal, but constant concentration over time. And this is your system in equilibrium. This is what system in equilibrium means. So the position of equilibrium is very important to indicate the direction of the reaction. So if the equilibrium goes to the right, then this means that, see, if your equilibrium here goes to the right, then this means that you are forming your product. And if your equilibrium goes to the left, then this means that you are forming your reactants. So this is what we mean by the direction of equilibrium. The direction of equilibrium tells me which side of the reaction is favored. Is it the product or is it the reactant? There is a way to know this, so I'll show it to you as we proceed. First, let's go ahead and start defining the equilibrium constant of the reaction. So the equilibrium constant of the reaction is simply representing the chemical reaction, and it's the relationship between the products versus the reactants. So if we have a chemical reaction in here, the A, B, C, and D, this is the number of moles, indicates the number of moles, which is the complete balanced equation. So you have your reactants on this side, you have your product on this side, and this is the equilibrium arrow. So if you have an equilibrium arrow, then you can express this reaction in terms of equilibrium equation. So the equilibrium constant is K. This is what the equilibrium constant is. And the equilibrium constant is always the concentration of the products divided by the concentration of the reactants. Okay, now what are the concentration of the products? We know that the products are C and D. So it's equal to the concentration of C, and always it's very important to balance the chemical equation so that you take into consideration the coefficients that you have for the C and the D. So it's the concentration of C to the power small c multiplied by the concentration of D to the power D divided by the concentration of the reactant. So this is the concentration of A to the power A multiplied by the concentration of B to the power B. Okay, so this is the equilibrium constant of the reaction. When you are reporting the equilibrium constant of the reaction, A, B, C, and D, they should be either gas or liquid or aqueous to be considered. If they are solids, then their concentration is 1. You take them out of the equation. Okay, so let's say, for example, in the chemical equation, if I have sodium solid, so if I have sodium solid in there, all solid reactants or products, they do not contribute to the equilibrium constant. So sodium solid has a concentration equal to 1. If I have, let's say, for example, copper solid, then the concentration of copper is equal to 1. So in order to take the components of a chemical equation into consideration for the equilibrium constant, the components of the chemical equation, they have to be either in the gaseous state or the liquid state or the aqueous state, not the solid. So if there's any component in there that is a solid, you just skip it from the equation. So let's say D was sodium, you just take the D out, okay? Because now its concentration is equal to 1. Let's have an example. So write the equilibrium constant expression at room temperature for the following equation. First of all, I have to make sure that my reaction is balanced. So this is a balanced reaction. And then I look at the states. I have gases, so both I can express them in terms of the equilibrium constant. It's the concentration of the products divided by the concentration of the reactants. Okay, so the products is the NO2. This is the concentration of NO2, and its coefficient is squared because the NO2 is 2 moles of NO2 there. And that is divided by the concentration of the N2O4. I have no coefficient. This is going to be 1. So I have 1 in here. So that is going to be to the power 1, which is, you can skip that. It's the same thing as nothing. So this is going to be the equilibrium constant expression for this chemical reaction. Let's have another example. So all of these, this is gases, gases, gas, and gas. So I can take all of those into consideration. It's the concentration of the products divided by the reactants. So the products are the nitrogen and the water. So this is going to be the nitrogen multiplied by the water. And it's going to be squared because of the 2 coefficient there, divided by the concentration of the NO squared multiplied by the concentration of the hydrogen squared. Another example, K, it's the concentration of the products to the reactants. S is a solid, right? So I cannot take it into consideration, but I have to take the gas states into consideration in the equilibrium expression. So it's the concentration of the SO2 divided by the concentration of the oxygen only, not the S, because S concentration is equal to 1. So I just skip it from the equation. Equilibrium expression there, I'm going to skip the copper from the equation and the iron from the equation. So the only two components in this equation that's going to contribute to the equilibrium constant are the concentration of the FeSO4 to the concentration of the copper sulfate. So as long as the temperature does not change, the equilibrium constant K will have a constant value. And I can use K to determine the equilibrium position in there. Of the reaction. I know that K is the concentration of the product divided by that of the reactants, right? So if K is large, this means that the concentration of the product is high. Concentration of the product is high. I know that the product lies on the right side, so equilibrium will be pushed to the right. And if K is a small value, then in this case, the equilibrium is going to be pushed to the reactant side, so it's going to be pushed to the left. Le Chatelier principle. So, Le Chatelier principle, this is a scientist who discovered that if a system at equilibrium is disturbed, it will shift in a direction to minimize the disturbance and restores equilibrium. So there are factors that affect the direction of the equilibrium. And the factors are the concentration of the reactants and the products, the reaction temperature, and the catalyst. So in general, Le Chatelier principle, it predicts the direction of equilibrium, which is the shift away from the side to which something is added and towards the side to which something is removed. This is what Le Chatelier principle is. The system at equilibrium, if it is disrupted, it will shift in a direction just to minimize the disturbance. So let's consider the factors that affect the direction of equilibrium. The first factor is the concentration. And this is the reaction over here. We are reacting phosphorus trichloride with chlorine in order to get phosphorus pentachloride, PCl5. So the question is, what is the direction of equilibrium, or predict the direction of equilibrium if I increase the concentration of the chlorine? So if the concentration of the Cl2 is added. Whenever you have a question like this, you want to figure out the direction of equilibrium. So to do this, we're going to use our hands. Our left hand is going to represent our reactants, and our right hand is going to represent our product. Any change in the concentration, we will represent this by simply lowering our hand or raising our hand. So chlorine is in the reactants, right? So if chlorine in the reactants, then I'm increasing the concentration of the chlorine as it is saying over here, chlorine added. So I'm just going to go ahead and raise my left hand. The direction of equilibrium is going to go towards the poor side. And this is what I meant by the system is going to react in the opposite. So if the system at equilibrium is disturbed, it will shift in a direction just to minimize the disturbance, and it's going to restore equilibrium. So now the equilibrium is going to go towards the right. So if chlorine is added, we would say that the equilibrium is going to shift. The equilibrium is going to shift towards the right once I am adding the chlorine from the left. Okay, let's have another example. PCl3. So PCl3, I'm removing it. Put your hands together again. And PCl3 is in the reactants, right? So if I'm removing it, then my left hand I'm just going to lower it because I am decreasing the concentration of the reactants. So my equilibrium is going to go to the other side, to the poor side. So it's going to go towards the left. So the equilibrium here is going to shift towards the left. So equilibrium was going to shift towards the left. So if it shifts toward the left, I'm just going to represent it by an equilibrium arrow going towards the left more, and another equilibrium arrow going towards the right. For the first case, I'm representing it by an equilibrium arrow going to the right and a small equilibrium arrow going to the left. You can easily see over here that the reaction for the first one is favored for the product. The reaction for the second one is favored for the reactants. This means that I need to start with PCl5 as my reactants, and now the chlorine and the PCl3 are going to be my products. So we're going to use the same hand method in order to determine the direction of equilibrium. In this example, I'm reacting iron oxide, this is a solid, okay, with carbon monoxide to get iron liquid and CO2. Guys, solids have no effect on the direction of equilibrium. Whether you increase their concentration, decrease their concentration, they have no effect. So if I am adding iron oxide, you go see iron oxide is a solid, so you say that since it's a solid, it does not affect the equilibrium of the reaction because its concentration is always equal to 1. So Fe2O3 is a solid, implies it does not affect the direction of equilibrium in there because the concentration of Fe2O3 solid is equal to 1. So since the concentration is equal to 1, it doesn't matter if I add it or if I take it out. It doesn't matter. The direction of equilibrium will be the same. It won't be affected. Now removing carbon dioxide. Where is carbon dioxide? Carbon dioxide is in the products. So put your hands together again. Removing carbon dioxide, you're going to lower your right hand, okay? So lower your right hand, and your equilibrium is going to go towards the reactants. It's going to push to the right. So we would say that the equilibrium here is going to be pushed to the right from the reactants to the products. So equilibrium will be pushed to the right. It's gonna go from the reactants, always give to the poor, okay? To the poor side. So reactants to the products. Okay. Removing carbon monoxide. So removing carbon monoxide, where's carbon monoxide? It's in the reactants. So put your hands together. Lower your left hand. Then the direction of equilibrium is going to be pushed to the left. It's going to go from the products to the reactants. So here is the equilibrium. Direction will be pushed to the left. So it's going to go from the products to the reactants. The second factor that affects the direction of equilibrium is the temperature. So it's very important to know what type of reaction you are working with, okay? What type of reaction I mean, is it endothermic or exothermic? Because you know that endothermic reaction means that the heat is in the reactants, and the exothermic reaction means that the heat is in the product, okay? So there are two conditions in there. So when the temperature of the reaction is increased, because you're going to have a reaction, and the reaction can be either endothermic or exothermic, and it's going to tell you, okay, the heat of the reaction is added. So heat of the reaction is added, you just check where is the heat. Is it in the reactants or is it in the products? And then we're going to apply the same hand method in there just to indicate if the heat is added or if the heat is removed. So if the reaction is endothermic, the heat is in the reactants. Yes. So put your hands together. Heat is in the reactants, right? And we said that heat is added. So you are going to raise your left hand. So you know that the position of the equilibrium is going to shift towards the product. I don't want you to memorize. I want you to practice this. You should get the same answers as I have over here. So if the reaction is exothermic means that the heat is in the product, right? So we said heat is added. So raise your right hand. If you raise your right hand, then your direction of equilibrium is going to go towards the reactants. So it's going to shift towards the reactants. On the other hand, when the temperature of the reaction is decreased, this is what it means, because in the given, it's going to tell you, are we increasing the temperature, or are we decreasing the temperature? So increasing the temperature means that I am adding heat. Decreasing the temperature means that I am removing the heat. So removing the heat, you want to know what type of reaction you are working with. Is it an endothermic reaction or is it an exothermic reaction? So you put your hands together. If the heat is removed, heat is going to be in the reactants. So you are going to lower your left hand. Lower your left hand, and your direction of equilibrium is going to push now towards the reactant. So it's going to push towards the left. If you have an exothermic reaction, heat now is going to be in the product. So if it's in the product and heat is removed, I want you to lower your right hand. So the direction of equilibrium is going to push towards the products. Let's have an example. Consider the following endothermic reaction. So see, I am telling you here that the reaction is endothermic. So endothermic reaction means the heat is in the reactants, so that you would know what's going to happen if you add or remove heat. So what happens to the direction of equilibrium when the equilibrium mixture is heated, right? So if the equilibrium mixture is heated, what does that mean? Heated means that I am increasing the heat. The heat is in the reactants, so I want you to put your hands together, raise your left hand. So if you raise your left hand, the equilibrium position will shift towards the right, just to use the extra heat that you added up, okay? So the equilibrium position is going to shift towards the right. So it's going to go from the products to the reactants, just to use up the added heat. Okay? So if NO2 gas is added, figure out where NO2 is. NO2 is in the reactants. So I am adding NO2. So I am increasing now NO2. So if I am adding NO2, put your hands together, you guys, and raise your left hand. Then your direction of equilibrium is going to go towards the right. Try just to use up the added NO2. So the equilibrium position is going to shift towards the right in order to use up the extra NO2 that you added. If some ammonia is removed from the equilibrium mixture, so look at the ammonia and say ammonia is in the product. So I am decreasing the concentration of the ammonia. So put your hands together and lower your right hand. Then your direction of equilibrium is going to be pushed again to the right to replace the ammonia that is removed. So the equilibrium position is going to shift towards the right in order to replace whatever we removed, the ammonia that is removed. Okay? The effect of the catalyst. The catalyst does not change the direction of equilibrium. The catalyst only speeds up the reaction. So whether you increase the concentration of the catalyst, you decrease the concentration of the catalyst, it really doesn't matter. The catalyst speeds up the reaction, but it does not change the position of the equilibrium. So the position of the equilibrium remains constant, remains the same. Let's have an example over here. So, okay, we have this reaction. This is an endothermic reaction, similar to the one before. So it's an endothermic reaction. It tells me what happens to the direction of equilibrium when the catalyst is added. I would say that equilibrium position will not change. So the equilibrium position will not change. Okay, let's go ahead and have more problems in there. So this is what you are going to see, a chemical reaction. And I don't even have to tell you this is an exothermic reaction. You look at the delta H and you see that it is negative. Then you know that it is an exothermic reaction. And if it's an exothermic reaction, then heat is going to be in the product. Then you know where's the position of the heat in there. So it says that determine whether each of the changes below would cause the equilibrium above to shift to the left, right, or have no shift. Adding nitrogen. So where is nitrogen? Nitrogen is in the reactants. I am increasing the concentration of nitrogen. Put your hands together, raise your left hand. Then the direction of equilibrium is going to shift towards the right. So it's going to shift towards the right. Please practice this. And if you have any questions, you let me know. Okay? If I'm increasing the temperature, so you look at the heat. Where is the heat? The heat is in the product. So if I'm increasing the heat, raise your right hand. Then the direction of equilibrium is going to shift to the left. So it's going to shift to the left. If you add a catalyst, nothing is going to change. So there's going to be no shift. And if you remove hydrogen, removing hydrogen means that you're decreasing the concentration of the hydrogen. So lower your left hand. Then your direction of equilibrium is going to shift to the left. Always the direction of equilibrium is going to go towards the poor side. Okay? So towards the side that is poor. This is another example. This is again an exothermic reaction because heat appears in the products. So what happens when we add oxygen? So if you add oxygen, you increase the concentration of oxygen. Raise your right hand. So your reaction is going to shift towards the right. You would increase the temperature. So increasing the temperature, you're going to raise your right hand. Now it's going to shift to the left. Add a catalyst, there will be no change or no shift. And removing the SO3. So if you decrease the concentration of the SO3, lower your right hand and your direction of equilibrium is going to shift to the right. Okay, this is an endothermic reaction now, so it's an endothermic reaction. So what happens if I remove oxygen? So decrease or lower your left hand. Your direction of equilibrium is going to shift towards the left. So this one is going to shift towards the left. You're increasing the temperature, so raise your left hand, then your direction of equilibrium is going to shift to the right. Add a catalyst, there will be no shift. And if we add the nitrogen monoxide, NO is in the products. So I want you to raise your right hand. Your direction of equilibrium is going to shift to the left. Okay, guys, so this is the end of the chapter. Go ahead and practice your homework problems. The key for the homework is posted to eCampus as well. Look at the key. If there's anything that you don't understand, please don't hesitate to let me know.